We are creating an absolutely mind-boggling amount of data every single day. We're talking petabytes of information. It's an explosion that just completely dwarfs what any single computer could ever hope to handle. So how in the world do we manage this data deluge? Well, let's dive in.
And really, this is the question that started it all. I mean, think about it. What do you do with a file that's, say, 100 terabytes? It's just not going to fit on your hard drive or even a massive server's hard drive. How do you store it? And more importantly, how do you actually work with it? This is the fundamental challenge that forced a completely revolutionary solution. You see, as our datasets started ballooning into the petabyte range, and remember, a petabyte is 1,000 terabytes, the old way of just buying a bigger, more powerful machine, well, that just stopped working. It became impossible. We needed a totally new approach. And that's where distributed file systems enter the picture. The idea of storing data across a whole network of computers instead of just one.
And the hero of our story today? It's HDFS, which stands for the Hadoop Distributed File System. It was literally designed from the ground up to solve this one massive problem: how to reliably store unbelievably large files across huge clusters of computers. So what's the magic here? What makes HDFS tick? It really boils down to three core ideas. First, it's built for enormous files. We're not talking gigabytes, we're talking terabytes and petabytes. Second, it's designed for what's called streaming data access. The best way to think about this is write once, read many. You load your massive dataset, like years of website logs, and then you analyze it over and over again. You're not going in and tweaking old records. And third, and this was a total game changer, it runs on cheap, off-the-shelf commodity hardware. We're talking regular, inexpensive computers, not some crazy expensive specialized supercomputer. Okay, so to really get how this works, we need to peek inside an HDFS cluster. The whole thing operates on what's called a master-slave architecture. It's really simple. Just think of it as one manager who's in charge and a whole team of workers who do all the heavy lifting. And this is where it gets really clever, this clear division of labor. On one side, you've got the master, the name node. This is the brain of the whole operation. It manages everything. It keeps track of all the files, handles all the administrative tasks, and most importantly, it knows exactly where every single piece of data is located. Then you have the slaves, the data nodes. They're the brawn. They are the workhorses that actually store the data, do the reading and writing, and carry out the tasks the name node gives them. Now let's break down what that means for the actual hardware. The name node, our brain, needs to be a pretty beefy, reliable machine with a ton of RAM. Why? Because it holds all the metadata, basically the address book for all our data, and it keeps that entire address book in memory for super fast access. The data nodes, on the other hand, the brawn, they can be those inexpensive commodity machines we talked about, because their main job is just to store the actual chunks of data. So how does HDFS actually pull this off? How does it manage these enormous files and, crucially, keep them safe? Well, the secret to its power lies in two really simple but powerful concepts: blocks and replicas. Let's see how they work. Okay, here's the play-by-play. A huge file shows up at the cluster. The name node, our brain, immediately gets to work and starts chopping that file up into big, uniform chunks called blocks. By default, these are 128 megabytes. Then it starts dealing these blocks out to all the different worker data nodes in the cluster. And finally, the data nodes themselves are told to make copies or replicas of the blocks they've just received. But hang on. Why go through all that trouble? Why take a perfectly good file and slice it into potentially thousands of little pieces? It sounds like a lot of extra work, doesn't it? Well, the answer is all about speed and parallelism. If you try to read one single 100 terabyte file, it's a slow, sequential process. But if you break it into thousands of blocks, spread across hundreds of machines, you can have all of those machines read their little piece of the file at the exact same time. It's a classic divide and conquer strategy, and it's what makes big data processing actually possible. Okay, so the blocks are for speed. That makes sense. But why make extra copies? Isn't that just a massive waste of disk space? This part is all about safety. Remember, HDFS is designed to run on cheap commodity hardware. And what does cheap hardware do? It fails all the time. If a data node crashes and you only have one copy of a data block on it, poof, that data is gone forever. Replication is the system's insurance policy. It guarantees that even if a machine dies, there are other copies of its data safe and sound on other machines in the cluster.
This is the essence of fault tolerance.
And the magic number for that insurance policy? By default, it's 3. For every single block of data, HDFS makes 2 extra copies and scatters them across the cluster for ultimate safety.
So how does the brain, the name node, even know that a worker has crashed? It uses this simple but brilliant little mechanism called a heartbeat. Every few seconds, each data node sends a tiny signal to the name node that basically says, "Hey, I'm still alive, everything's good over here." If the name node stops hearing that signal from one of the data nodes, it just assumes it's dead, marks it as such, and immediately starts making new replicas of the blocks that were on that failed machine. It's self-healing. So, as you can see, HDFS is incredibly powerful, but like any tool, it's not the right choice for every single job out there. It has some very clear strengths and also some pretty important weaknesses you need to understand. So let's recap the good stuff. As we've seen, it is unbelievably fault-tolerant and reliable because of that replication. Your data is safe. It's also super easy to scale. Need more storage? Just add more cheap machines to the cluster. And by chopping up files into blocks, it makes finding and reading data inside those massive files way, way faster. But it is not a silver bullet. First, it is terrible for what we call low latency access. Think of HDFS as a giant freight train. It can move a mountain of stuff, but it takes a long time to get going and a long time to stop. If you need the speed of a sports car, quick, real-time responses in milliseconds, HDFS is absolutely the wrong tool. Second, it has what's known as this small file problem. Because the name node has to keep that address book for every single file in its memory, it's fine for a few huge files. But if you try to store millions or even billions of tiny little files, you will completely overwhelm the name node's memory and bring the whole system to its knees. And really, this quote sums up the entire philosophy of HDFS perfectly. It is built for one thing and one thing only: high throughput. It's designed to be that freight train, moving the maximum amount of data over a period of time, and it is perfectly happy to sacrifice the zippy, low-latency speed of a sports car to achieve that goal. So there's no question that HDFS was a truly revolutionary solution for the big data challenges of its time. But as data keeps evolving, getting faster, more complex, and coming from everywhere at once, it leaves us with a really fascinating question to chew on. What kind of system, what kind of new idea will we need to invent to solve the data problems of tomorrow?